So far, we have mainly looked at congruence for polygons. Polygons are special because they're determined by line segments. These line segments give polygons easily defined distances and angles to measure and compare. For a more complex shape with curved sides, the situation is a little different, unless the shape has special properties, such as being a circle. In previous lessons, we established a definition of congruence. One figure is congruent to another if it can be moved with translations, rotations, and reflections, or a sequence of these to fit exactly over the other. In the figure, triangle A is congruent to triangles B, C, and D. A translation takes triangle A to triangle B, a rotation takes triangle B to triangle C, and a reflection takes triangle C to triangle D. Rigid motions do not change distances between points, so if figure 1 is congruent to figure 2, then the distance between any pair of points in figure 1 is equal to the distance between the corresponding pair of points in figure 2. In today's lesson, let's find ways to test congruence of interesting figures. Polygons are special shapes because once we know the vertices listed in order, we can join them by line segments to produce the polygon. This is important when performing rigid transformations. Because rigid transformations take line segments to line segments, once we track where the vertices of a polygon go, we can join them in the correct order with segments to find the image of the polygon. Trapezoids ABCD and A', B', C', D' are congruent. Draw and label the points on A', B', C', D' that correspond to E and F. Draw and label the points on ABCD that correspond to G' and H'. Draw and label at least 3 more pairs of corresponding points. What strategies did you use to mark the corresponding points? You may have used the grid and the corresponding vertices to keep track of distances and then placed corresponding points in the right place. You may have used your tracing paper and rigid motions to take one polygon to the other. Take a look at these ovals. In your groups, come up with one mathematical question you could ask about these ovals. Are any of these ovals congruent to one another? Explain how you know. You may have drawn a rectangle around the ovals and then determined the length of the rectangle and the width of the rectangle to determine the general size of the oval. Then, using your patty paper, you could carry out a sequence of rigid transformations to prove that the top 2 ovals can be lined up perfectly over one another. The smaller ovals are also congruent to one another. This can be proven if you can determine the sequence of rigid transformations that takes the oval on the lower left corner to the oval next to it. This can be accomplished through a 90-degree clockwise rotation. You can use your patty paper to prove to yourself exactly where that center of rotation is. If we consider the lower left corner of the grid to be 0, 0, then we could label this point 3, 3. Here are 2 congruent shapes with some corresponding points labeled. Draw the points corresponding to B, D, and E, and label them B', D', and E'. Draw line segments AD and A', D', measure them. Do the same for segments BC and B', C', and for segments AE and A', E'. What do you notice? Do you think there could be a pair of corresponding segments with different lengths? Explain. The lengths are the same. The rigid transformations of the plane used to show the congruence of these shapes do not change distances between points. So the distance between A and D, for example, is the same as the distance between A' and D'. The same is true for the other pairs of corresponding points. The segments connecting these points are all shown here. Rigid transformations do not change distances between points. Corresponding segments in the 2 congruent figures must have the same length. Up to this point, you've mostly worked with simple figures. That is, figures which are individual and complete and not naturally divided into parts. Are these faces congruent? Explain your reasoning. Show your thinking by marking up the figure and explaining your reasoning in words. The faces are not congruent. Although the parts of the faces, the outline, the eyes, the mouth, are congruent taken one by one, the faces as a whole are not congruent. The 2 oval outlines of the face sit in 8-unit by 10-unit rectangles, and they are congruent as can be seen by translating the left face outline 10 units to the right or reflecting over the center vertical line on the grid. All 4 eyes in the 2 faces are also congruent. This can be shown using horizontal translations. The 2 mouths are congruent, also using a translation, but this time the translation has a horizontal component. 10 units to the right, and a vertical component about half a unit down. While the individual parts are congruent, the faces as wholes are not. In the figure on the left, the eyes are 1 unit apart. For the figure on the right, they are almost 2 units apart. The mouth on the left is about 1 unit below each eye, while the mouth on the right is more than 1 unit below each eye. The mouth on the right is also closer to the outline of the face than the mouth on the left. In each case, there is a pair of corresponding points in the two figures whose distances are different. This means that the figures are not congruent. Two figures are congruent when there is a sequence of translations, rotations, and reflections matching up one figure with the other. To show that two figures are not congruent, it is enough to find corresponding points on the figures which are not the same distance apart, or corresponding angles that have different measures. The distance between pairs of corresponding points in congruent figures is the same. This says that corresponding side lengths on polygons have the same length, but it applies to curved figures also, or to any pair of points, not necessarily vertices, on polygons. Some figures are made up of several parts. For example, these two designs are each made up of 3 circles. All 6 circles are congruent, as we could check using tracing paper. But in the left design, each circle touches both of the other 2, but this is not true in the design on the right. The distances between any 2 circle centers in one design will be different than the distances between any 2 circle centers in the other design. Therefore, overall, these figures are not congruent. To show two figures are congruent, you align one with the other by a sequence of rigid transformations. This is true even for figures with curved sides. Distances between corresponding points on congruent figures are always equal, even for curved shapes. For example, corresponding segments AB and A'B' on these congruent ovals have the same length. To show two figures are not congruent, you can find parts of the figures that should correspond but that have different measures. For example, these two ovals don't look congruent. On both, the longest distance is 5 units across, and the longest distance from top to bottom is 4 units. The line segment from the highest to the lowest point is in the middle of the left oval, but in the right oval, it's 2 units from the right end and 3 units from the left end. This proves that they are not congruent. Today we learned how to use distances between points to decide if two figures are congruent. Are figures A and B congruent? Explain your reasoning. These figures are not congruent because if they were, the longest horizontal distances between 2 points would be the same. However, for A, it is less than 4 units, and for B, it is about 4 units.